This podcast was created as a supplemental learning resource for this course. The content is based on assigned course materials, including open educational resources, textbook chapters, instructor-developed explanations, examples, and applications connected to course topics. AI tools were used to help transform course material into a conversational podcast format, including the use of AI-generated narration. The AI narration is intended to make the material more engaging, accessible, and flexible for students. However, the podcast should not replace careful reading of assigned materials, reviewing course lectures, or completing course activities. Any interpretations, examples, or explanations included in the podcast are provided for educational purposes and are the responsibility of the instructor. Students should rely on the assigned readings, course lectures, and official course materials as the primary sources for exams, assignments, and class discussions.
Usually when you break your arm, the diagnosis is just, well, it's incredibly straightforward.
Right.
The doctor takes an X-ray, pulls up the image, and just points to that jagged, undeniable white line running through the bone.
Exactly.
There's this definitive cause and effect right there on the screen. The impact broke the bone. You cast it, and it heals. I mean, the physical world, when we can measure it with precision, offers a very comforting kind of binary logic.
Oh, absolutely. We crave that level of certainty. We're inherently pattern-seeking creatures, And when we can point to variable A and definitively say it caused outcome B, we feel a sense of control over our environment.
Yeah, that makes sense.
We want human behavior to fit into those same neat laboratory-controlled boxes, but as you're learning in your psychology course, it rarely does.
Right, because the moment you step out of a pristine laboratory and into the messy, chaotic, just overlapping realities of human lives, that X-ray machine kind of shatters.
It really does. You can't just isolate a single human emotion or behavior in a vacuum.
No, you can't. And let me paint a picture for you, the listener, of just how murky this gets. So in the early 1970s, a psychologist named David Rosenhan gathered a group of perfectly sane people, friends, colleagues, a pediatrician, a painter.
Such a wild study.
It's crazy. He instructed them to walk into different psychiatric hospitals across the country and tell the admission staff a very specific lie.
Right.
They were to say they were hearing voices, and those voices were saying empty, hollow words like, thud.
And the premise was just brilliant in its simplicity. Because once admitted to the psychiatric wards, these pseudo-patients were instructed to completely stop faking any symptoms.
They just acted normal.
Yeah, they reverted to their normal behavior, spoke normally to the staff, and reported feeling absolutely fine.
And the result is, frankly, terrifying. Not a single one of these sane individuals was detected by the hospital staff.
Which is mind-blowing.
They were all diagnosed with schizophrenia. They were kept in these wards for an average of, 19 days. And the wildest part is that some of the actual patients in the ward figured out they were faking, but the doctors and nurses never did.
Right, the patients were like, you're a journalist checking up on the hospital or something.
Exactly. And when they were finally discharged, their files didn't say they were cured. The file said schizophrenia in remission. That label stuck to them forever.
Which completely upended the psychiatric establishment of the era. I mean, it forced the field to confront the reality that diagnostic labels could entirely dictate how a person's behavior was perceived.
Oh, for sure.
Normal behaviors, like taking notes in a journal, were pathologized by the nursing staff as, quote, writing behavior, like it was a supposed symptom of their illness.
So the reason we're starting with Rosenhan's study as you dive into Chapter 6 of your OER textbook today is because of a massive realization. I always assumed the biggest, most earth-shattering discoveries in psychology came from people in white coats running highly controlled, randomized experiments.
A lot of people assume that.
But Rosenhan's study, one of the most famous in psychology's history, wasn't an experiment at all. There was no control group. There was no manipulated independent variable in a lab. It was just observational.
That is the crucial threshold we're crossing in today's deep dive. While true experiments hold this privileged place in science because they can isolate direct cause and effect, the reality of studying human beings demands a wider toolkit.
We need more than just the X-ray.
Exactly. Non-experimental research is not a fallback or a lesser form of science. It is an absolute necessity. The defining characteristic is simply the lack of manipulation.
So if you aren't tweaking something, it's non-experimental.
Right. If a researcher is not actively altering an independent variable to measure its impact on a dependent variable, they are in the realm of non-experimental research.
So no manipulation, no true experiment. You're just measuring the world as it already exists. And to really hammer home how foundational this is, let's look at a few more heavy hitters from your reading.
Good idea.
Take Stanley Milgram's obedience study. The cultural footprint of this study is massive. Participants sit in front of this terrifying-looking shock generator and are told by a stern authority figure in a gray lab coat to administer increasingly high voltages to another person in the next room every time they answer a question incorrectly.
And the participants genuinely believed they were delivering agonizing shocks. They're listening to the screams of the person next door who is, an actor.
Right, no one was actually getting shock.
No, thankfully. But Milgram discovered that a deeply unsettling majority of people, around 65%, were willing to push the dial all the way to a lethal voltage simply because an authority figure told them the experiment required it.
It's so dark, but look at the architecture of that original foundational setup. Milgram wasn't splitting people into groups and manipulating a variable.
No,
He wasn't comparing a stern scientist group to a friendly scientist group in that first iteration. He simply built a highly pressurized environment, placed individuals inside it, and just observed what they did. He measured the dependent variable, which was the maximum shock delivered, without an independent variable to manipulate.
Or consider the realm of cognitive psychology and memory. Elizabeth Loftus and Jacqueline Pickrell fundamentally altered our understanding of the brain with their Lost in the Mall study.
Oh, this one is fascinating.
It really is. They wanted to know if it was possible to implant a completely fabricated memory into a person's mind so vividly that the person would believe it genuinely happened.
And the methodology they used is so clever. They contacted the older relatives of the participants and gathered 3 true stories from their childhoods.
Real baseline memories.
Then, the researchers fabricated a 4th story, a detailed account of the participant getting lost in a specific shopping mall at age 5, crying, and being rescued by an elderly woman. They presented all 4 stories to the participants in a booklet and asked them to write down what they remembered.
And the results were staggering. Over the course of a few weeks and some follow-up interviews, a quarter of the participants began to recall the fake mall event.
A whole 25% just created a memory.
Yeah, and they even added their own sensory details to the false memory. They confabulated entirely new details describing the clothing of the elderly woman or the specific stores they walked past.
Wow.
It demonstrated the profound malleability of human memory. But again, structurally, the researchers were taking descriptive measurements. They were observing the phenomenon of memory creation in a real-world context rather than running a randomized control trial.
There's another classic example in the chapter involving how much people actually enjoy thinking. John Cacioppo and Richard Petty developed a scale called the need for cognition.
Right, I love this one.
They hypothesized that some people just intrinsically find joy in solving complex mental puzzles, while others actively avoid heavy cognitive lifting unless it's strictly necessary. To validate their scale, they administered it to 2 distinct groups, university professors and factory workers.
And the researchers assumed, quite logically, that individuals who chose a life of academia would naturally score higher on a scale measuring the enjoyment of complex thought. And the data supported that assumption.
Which makes sense.
It does. But the critical distinction, for our purposes, is that they did not assign these roles. They didn't randomly select 100 people, force 50 to become professors, and 50 to work on an assembly line, and then test them years later.
No, they just observed pre-existing groups. Nature or society had already sorted the participants. The researchers just brought the yardstick.
Exactly.
So if we look at the whole landscape, Milgram's shocks, Loftus's false memories, Cacioppo's cognition scale, and Rosenhan's psychiatric infiltration, we have to ask a hard question about the strength of this evidence, like how loud is the signal we're getting from these studies?
And that brings us to the concept of internal validity. Internal validity is a measure of confidence. It asks, how confident can we be that the relationship we're seeing between variables is genuine and not the result of some unseen outside force?
I picture internal validity as a master volume dial on a high-end stereo receiver.
Oh, I like that.
This dial dictates how loudly and clearly a researcher is allowed to shout, "Variable X definitely caused variable Y." When you run a true, pristine experiment, you get to crank that volume dial all the way up to 10.
Because you have total control.
Right. You have a highly controlled lab, you randomly assign your participants, you manipulate one single variable, and you hold everything else constant. By stripping away the noise of the outside world, you can clearly hear the signal. The volume is deafening. The manipulation caused the result.
That analogy holds up really well. In non-experimental correlational studies, that volume dial is turned down significantly, perhaps resting at a 2 or a 3.
This is pretty quiet.
Yeah, you're observing that two things happen together. Perhaps you notice that people who drink more coffee tend to have less severe asthma symptoms. The association is there, but you're listening to it through a wall of static.
Because you haven't controlled for anything else.
Exactly. You haven't controlled for their diet, their exercise habits, their genetics, or their stress levels. You cannot clearly hear the signal of causality over the roar of all the other potential environmental factors.
You also have quasi-experiments sitting somewhere in the middle of that dial, maybe at a 5 or 6. They have some experimental features but lack a crucial element, usually random assignment.
Right.
But this raises a massive red flag for me. If a true experiment is the gold standard, if turning the dial to 10 is the only way to get a perfectly clear signal, why on earth would any self-respecting scientist voluntarily turn the volume down? Why choose a weaker method?
Well, the answer is that the real world does not care about our desire for scientific purity. Researchers are bound by two immovable constraints: practical limitations and rigorous ethical boundaries. Let's examine the ethical barrier first.
Okay.
Suppose you're a neuroscientist studying the function of the frontal lobe, specifically how a severe localized trauma affects a person's ability to process complex language.
Okay, so to do a true experiment, I would have to recruit 100 healthy people, bring them into the lab, randomly assign 50 of them to a control group, and then forcefully inflict traumatic brain injuries on the other 50 to see what happens to their speech.
Which is an abhorrent violation of every ethical code in existence.
Yeah, please don't do that.
We cannot purposefully cause harm, inflict trauma, or intentionally degrade a human being's quality of life for the sake of gathering clean data.
So our hands are completely tied. The X-ray machine is locked in the closet.
Exactly. So we have to wait for nature, or a tragic accident, to manipulate the variable for us. We find individuals who have unfortunately suffered frontal lobe injuries in car accidents or falls, and we study their cognitive function after the fact, comparing them to healthy individuals.
We're observing pre-existing groups.
Right. We have turned the volume dial down on our internal validity, but it is the only morally permissible way to gather the data.
So pause and think about this for a second if you're listening. Put yourself in a researcher's shoes regarding a different scenario. You want to understand the long-term psychological impact of a catastrophic natural disaster on childhood development. Let's say a Category 5 hurricane.
You obviously cannot conjure a hurricane and randomly assign a neighborhood of children to be in its destructive path while keeping another neighborhood safe as a control.
No, you have to wait for a hurricane to happen, rush into the aftermath, and observe the variables as they naturally unfold.
Furthermore, beyond ethics, sometimes our goal isn't to prove a causal mechanism at all. Sometimes the goal is purely exploratory.
Just seeing what's out there.
Exactly. Before you can design an experiment to test a phenomenon, you have to know that the phenomenon exists, and you have to understand its boundaries. Descriptive, non-experimental research maps the territory so that later experimental researchers know where to dig.
So we use these methods because we have to and because they help us sketch the map. And one of the most complex maps psychologists have to draw is the map of human development over time.
Oh, definitely. Time is a tricky variable.
Tracking how people change as they age requires specific architectural designs. Developmental psychologists are essentially scientific time travelers, and they rely heavily on 3 specific non-experimental blueprints to track variables across the lifespan.
The most immediate and practical of these blueprints is the cross-sectional study.
Okay, how does that work?
The mechanism here is simultaneously testing 2 or more pre-existing age groups at a single frozen point in time. Imagine you want to investigate how short-term working memory capacity shifts as people transition into late adulthood.
Okay, so if I'm using a cross-sectional design, I don't have time to wait around. I'm going to recruit a group of 20-year-old college students and a group of 70-year-old retirees today.
Right.
I bring them all into the testing center this afternoon, administer the exact same computerized memory recall task, log the data, and compare the 2 groups. It's incredibly efficient. I can have a complete data set on aging in a single weekend.
It is efficient, but it contains a devastating trap.
Uh-oh.
Let's assume the data shows that the 70-year-old cohort performs significantly worse on the computerized task than the 20-year-old cohort. The immediate instinctual conclusion is that biological aging causes a decline in working memory.
Sure, that seems logical.
But because the independent variable age was not manipulated by the researcher, we have to look for lurking variables. And the most dangerous lurking variable in a cross-sectional study is the cohort effect.
A cohort is a group of people bound together by a shared historical and cultural experience, right? Like the generation you're born into shapes your brain.
Precisely. Consider the environmental differences. The 20-year-olds in your study have grown up as digital natives. Their brains have been wired since childhood to rapidly process information on screens, switch between digital tasks, and interact with computerized interfaces.
And the 7-year-olds grew up in an entirely different technological epoch.
So the crucial question is, are the 70-year-olds performing worse because the biological machinery of their brains is deteriorating? Or are they performing worse because they are navigating a computerized testing environment that is fundamentally alien to their developmental background?
Oh, wow. The generation gap doesn't just confound the data, it completely overwrites it. You literally cannot disentangle the biological effect of aging from the sociological effect of the era they were born in.
You really can't. To fix that, we have to stretch the study out. We move to the second blueprint, which is the longitudinal study.
The long haul.
This is the ultimate commitment to the scientific method. Instead of testing different people today, you take a single group of people and you stalk them through time. You test your 20-year-olds today. Then you pack up your files, wait 50 years, track down those exact same individuals when they are 70, and test them again.
The beauty of the longitudinal design is that it structurally annihilates the cohort effect. You're comparing a generation exclusively to itself.
Exactly.
If their memory scores decline 50 years later, you can be highly confident that the change is due to the internal aging process because their historical background and generational experiences have remained constant.
That's the theory, yes.
But wait, if longitudinal studies are the only way to actually strip out the cohort effect and give us a clean look at biological aging, I don't understand why any researcher would ever bother with a cross-sectional study. Are they just being lazy?
No, not at all.
Yeah.
It is entirely a matter of crushing practicality. A longitudinal study is a logistical nightmare.
Because it takes forever.
First, there's the investment of time. If you start a study on 20-year-olds and want to see how they behave at 70, you're committing to a half-century of waiting before you can publish your final conclusions. In the competitive world of academia, researchers need to publish frequently to secure tenure and funding.
You literally might die before your study finishes.
Exactly that. The original researchers often retire or pass away, requiring a new generation of scientists to take over the project. Funding grants dry up. But the biggest issue is participant attrition.
People dropping out.
All right, people drop out. They move across the country and don't leave a forwarding address. They lose interest, they pass away. If you start with 1,000 20-year-olds, you might only be able to locate 100 of them 50 years later.
And that messes up the data.
Oh, severely. The ones who survived and remained in the study might share specific characteristics like higher income or better health that skews your final data.
It's a brutal trade-off. You choose cross-sectional and get fast data ruined by cohort effects, or you choose longitudinal and get clean data that takes a lifetime and bleeds participants.
But there is a third option.
A masterstroke of research architecture called the cross-sequential study.
The cross-sequential design is a hybrid. It weaves together the immediate gratification of a cross-sectional study with the rigorous tracking of a longitudinal study.
Best of both worlds.
Exactly. Instead of tracking one group for 50 years or testing multiple groups just once, researchers recruit multiple age cohorts and track them all simultaneously for a much shorter, manageable duration.
Let's mentally map this out so the mechanism is completely clear for everyone listening. Imagine the year is 2026. You want to study how marital satisfaction changes from the honeymoon phase into midlife.
Okay, good setup.
You recruit 3 distinct cohorts. A group of people who have been married for 1 year, a group married for 5 years, and a group married for 10 years. You test them all today on 2026. That gives you your immediate cross-sectional data. You can publish a paper right now comparing the 3 groups.
But you do not stop there. You hold on to all 3 groups and you track them longitudinally for 5 years. You bring them all back into the lab in the year 2031.
Okay, let's look at what happens to the math here. In 2031, your original 1-year cohort has now been married for 6 years. Your original 5-year cohort has now been married for 10 years. And your original 10-year cohort has now been married for 15 years.
And here is where the genius of the design reveals itself. You now have 2 separate groups of people who have been tested at the 6-year marriage mark. You have the original 5-year group, who you tested back in 2026, and you have the new 6-year group, who just reached that milestone in 2031.
Oh, I see.
You can mathematically compare the 2026 data against the 2031 data. If the marital satisfaction scores at the 6-year mark are identical, regardless of which historical year they were tested in, you've proven that the cohort effect is minimal and the aging effect is real.
You essentially built a bridge over the generation gap, and you did it in 5 years instead of 15.
It's remarkably efficient.
It is an incredibly elegant way to isolate variables when time itself is the thing you're trying to study. But we don't always need to track changes over decades. Sometimes we want to look at the immediate collision of 2 behaviors right now.
Like a snapshot.
Yeah.
Yeah.
We want to measure the invisible tether between, say, a student's level of anxiety and their academic performance on a single Tuesday. That brings us into the math of relationships, specifically the mechanics of correlational research.
And to understand correlational research, we had to strip away a really common misconception. People often conflate correlational research with survey research, assuming that if you hand out a questionnaire, you're doing a correlational study.
Right, but that's not true.
No, correlational research is defined entirely by the lack of manipulation, regardless of where or how the data is collected.
You could be in a subterranean, climate-controlled laboratory measuring a participant's precise heart rate and pupil dilation, and as long as you aren't manipulating an independent variable to cause those physiological changes, you are conducting correlational research. You're just watching 2 variables float in space, measuring them, and seeing if they move together in any predictable pattern.
And when we gather that data, especially when dealing with quantitative variables, meaning anything we can attach a numerical value to, we need a way to visualize the chaos. We rely on the scatter plot.
Let's visualize this together. Picture a standard sheet of graph paper. Let's use an example of measuring a person's stress level against the number of physical health symptoms they've experienced in the past month.
Classic example.
The horizontal line along the bottom, the x-axis, represents a self-reported stress scale ranging from 0 on the far left up to 20 on the far right. The vertical line going up the side, the y-axis, represents the number of physical symptoms, headaches, stomach aches, insomnia ranging from 0 at the bottom up to 10 at the top.
So every single human being in your study is reduced to a single dot on this graph. If you interview participant number 1 and they report a stress level of 15, and they also report having 6 physical symptoms, you run your finger along the bottom to the 15, slide it up to the 6, and draw a dot.
You repeat this exhaustive process for all 200 people in your sample.
And when you step back and look at the paper, you won't see a single clean line. Because human beings are messy.
Very messy.
You will see a swarm of dots. But if there is a relationship between stress and physical illness, that swarm won't be entirely random. It will have a shape. The dots will cluster together, forming a general trend, tilting upward from the bottom left corner toward the top right corner.
To move from visual interpretation to hard mathematics, researchers calculate a specific statistic called Pearson's correlation coefficient, universally referred to as Pearson's R. This statistic measures the precise strength and direction of the linear relationship between the 2 variables.
And it's a very specific mathematical tool.
I think of Pearson's R as a measure of gravitational pull between the 2 behaviors.
That's a great way to conceptualize it.
The math always spits out a number somewhere between a perfect negative 1.00 and a perfect positive 1.00. The closer the number gets to the absolute poles, the ones, the stronger the gravity.
Right.
If the math calculates an R of 0.95, there's a massive gravitational pull, yanking all those scattered dots out of the swarm and aligning them into a tight, nearly perfect straight line.
Conversely, if Pearson's R calculates out to 0, there is a complete absence of gravity. The variables have absolutely no relationship. The dots scatter across the graph paper like buckshot.
Total chaos.
Exactly. Knowing a person's stress level provides you with 0 predictive power regarding how many physical symptoms they might have. The information is mathematically useless.
And the positive or negative sign in front of the number tells us about the direction of the relationship. A positive correlation A number greater than 0, moving toward a positive 1, means the variables move in tandem, like an escalator. As stress goes up, physical symptoms go up.
A negative correlation, moving toward -1, indicates an inverse relationship. They move in opposite directions, like a seesaw.
A great example of a negative relationship is the correlation between a student's test anxiety and their actual exam score. As the internal anxiety level spikes upwards, the final grade on the exam plunges downward.
Right. The scatterplot trend line would tilt sharply from the top left corner down to the bottom right corner.
When reading psychological literature, it's crucial to understand what numbers actually matter. Because human behavior is influenced by thousands of microscopic factors every second, we rarely see perfect 1.000 correlations outside of physics.
Oh, never in psychology. An R of 0.10 is generally considered a small effect. It's a weak gravitational pull. The dots are still very clouded, but there's a slight tilt.
Okay, so 0.2 is small.
Right. An R of 0.30 is a medium effect, and an R of 0.50 or above is considered a large, robust correlation.
So if you see a headline screaming about a new study linking eating blueberries to improve memory, and you dig into the methodology and see an R of 0.12, you know not to base your entire diet around it.
Exactly. The relationship exists, but it's faint.
And understanding those numbers is just the first layer of defense, because the moment you start interpreting statistical data, you walk straight into a minefield of traps and logical fallacies.
Statistics are incredibly powerful, but they're also completely literal. They only do exactly what you ask them to do. The first major trap researchers fall into is forgetting the fundamental limitation of Pearson's R. It is exclusively designed to measure straight lines.
Linear relationships only.
Exactly. It is mathematically blind to curves.
This is where the math actively lies to you if you aren't paying attention. Let's look at the relationship between the number of hours you sleep every night and your reported level of clinical depression.
This is a perfect example.
If you restrict a person's sleep to only 3 or 4 hours a night for a month, their depression levels will likely skyrocket. If you increase their sleep to a healthy, optimal 8 hours, their depression levels will drop to their lowest point.
But the relationship does not continue linearly. If you force someone to sleep 14 hours a day, keeping them bedridden, their depression levels will spike upwards again. Hypersomnia is a major depressive symptom.
So if you plot that on our graph paper, it doesn't form a line tilting up or down. It forms a massive swooping curve, a giant U shape. The outer edges are high depression, the middle is low depression. The relationship is profound, highly predictable, and undeniable.
But if you feed that raw data into a computer and ask it to calculate Pearson's R, the algorithm will attempt to draw a single straight line through a U-shaped scatter plot. The line of best fit will simply run perfectly flat across the middle of the curve.
It just draws a flat line.
Yes, the computer will spit out an R of 0. It will mathematically declare that there is absolutely no relationship between sleep and depression.
It's a catastrophic failure of analysis. The researcher would publish a paper saying sleep doesn't matter, completely missing the massive curve hiding in the data.
Which is why researchers are trained to visually inspect their scatter plots before they ever run the numbers. You have to look at the shape of the swarm before you ask the computer to summarize it.
The second trap is equally deceptive, the restriction of range. This occurs when a researcher sample does not capture the full, naturally occurring spectrum of the variables they're studying. When you zoom in too closely on a small patch of data, the broader trend becomes invisible.
Let's use an example involving music taste. Suppose there is a genuine, strong, negative correlation across the entire human population between age and the enjoyment of heavy metal music.
Okay.
If you survey people from age 10 all the way to age 90, the trend is clear as age goes up, preference for heavy metal goes down. The correlation might be a strong negative 0.60.
However, imagine a graduate student conducting this research who, for the sake of convenience, only distributes their survey to the undergraduates living in their campus dorm. Their entire sample consists of individuals between the ages of 18 and 21.
They took a massive downward-sloping graph and put a tiny magnifying glass over just one sliver of the x-axis.
Within that 3-year age bracket, the preference for heavy metal is going to vary wildly and randomly. Some 19-year-olds love it, some hate it. Because you've restricted the range of age, the data points within that tiny window look like a random, chaotic cloud.
And the graduate student calculates Pearson's R for their limited data set, and it comes back as 0. They conclude that age has no bearing on musical preference.
Which is entirely wrong.
Completely wrong. Not because their math was flawed, but because their architectural design artificially restricted the reality they were measuring.
Which brings us to the apex predator of statistical traps, the fallacy that is beaten into the head of every first-year science student on the planet. Correlation does not imply causation.
It is a cliché because it is the single most common error in human logic. We see two things happening in unison, and our brains instantly invent a story where one caused the other.
Let's look at an incredibly famous, absolutely real example. In 2012, a rigorous study analyzed data from dozens of countries and found a staggering positive correlation in R of 0.79 between a nation's per capita chocolate consumption and the number of Nobel Prizes awarded to its citizens.
A correlation of 0.79 is incredibly powerful. The nations whose populations eat the most chocolate genuinely, verifiably produce the most Nobel laureates. The statistical tether is undeniably real.
So, as a matter of national security and scientific dominance, should we be replacing school lunches with massive blocks of dark chocolate to rapidly engineer a generation of genius physicists and peacemakers?
Obviously not.
Handing a child a chocolate bar does not spontaneously imbue them with the ability to split the atom. The relationship is real, but it is not causal. And there are two distinct logical walls blocking us from claiming causation.
The first wall is the directionality problem. When two variables are correlated, the statistical math is a two-way street. It cannot tell you which variable is the engine driving the car and which variable is simply sitting in the passenger seat.
Think about the relationship between physical exercise and a positive mood. The data shows a strong positive correlation. But what is the direction of the arrow? Does going for a vigorous run flood the brain with endorphins, causing a positive mood? That's one highly plausible direction.
But consider the alternative. When a person is experiencing a major depressive episode, they suffer from profound lethargy and a lack of motivation. When a person is in a good mood, they feel energetic and capable.
So the mood might come first.
Exactly. Therefore, being in a positive mood might be the direct cause of a person deciding to go for a run. The mood causes the exercise. Simple correlational data cannot separate the engine from the passenger.
And then there is the second wall, the most insidious villain in all of observational research, the third variable problem. This is the scenario where neither X causes Y nor Y causes X. Instead, a hidden, entirely unmeasured factor variable Z is operating in the shadows, secretly pulling the strings on both of them.
Returning to our chocolate and Nobel Prize dilemma. If chocolate isn't causing genius, and genius isn't causing a craving for chocolate, what is variable Z?
The million-dollar question.
The most logical answer is a nation's overall wealth, its gross domestic product.
Oh, that makes perfect sense. A wealthy nation has citizens with enough disposable income to purchase luxury imported goods, like high-quality chocolate.
Right.
Simultaneously, a wealthy nation has billions of dollars to invest in state-of-the-art research facilities, elite university infrastructure, and highly funded education systems, which are the actual engines that produce Nobel laureates.
The wealth variable Z causes the chocolate consumption to rise. The wealth also causes the scientific achievement to rise. The chocolate and the prizes move together on the graph in a beautiful, synchronized dance, but they are completely independent of each other. They're both just reacting to the invisible gravity of wealth.
So, if the third variable problem is constantly lurking in the shadows, threatening to invalidate our conclusions, how do psychologists fight back? If we are ethically barred from running an experiment, are we just doomed to guess at what variable Z might be?
Not anymore. We level up the math, we move into the realm of complex correlations.
Complex correlational research is an acknowledgement that human behavior is almost never driven by a single factor. To get closer to the truth, researchers stop looking at variables in isolation and start measuring dozens of variables simultaneously, analyzing the entire ecosystem of behavior.
They built something called a correlation matrix. Imagine that instead of just asking a participant about their stress and physical symptoms, you give them a battery of tests. You measure their anxiety, their baseline self-esteem, their household income, the hours they sleep, their diet, and their extroversion.
That's a lot of data.
It is. A correlation matrix is a massive, complex grid that cross-references every single one of those variables against every other variable. It calculates a distinct Pearson's R for anxiety versus sleep, anxiety versus income, sleep versus self-esteem. It builds a sprawling web of mathematical tethers.
But simply looking at a tangled web doesn't solve the third variable problem. You have to untangle it mathematically. To do this, statisticians develop techniques of statistical control, primarily partial correlation and multiple regression.
Multiple regression sounds like something you need a doctorate in calculus to understand, but conceptually, it is incredibly intuitive.
Imagine you are a high-end music producer sitting in front of a massive mixing board in a recording studio. You are listening to a complex track with 30 different instruments playing simultaneously: guitars, a brass section, synthesizers, 3 drum kits, and layered vocals. But there is a terrible high-pitched feedback squeal ruining the entire song.
If you are relying on simple correlations, you're just standing in the room listening to the chaotic noise. You know the feedback is there, but you have no idea which of the 30 instruments is responsible.
But with multiple regression, you have access to the mute buttons on the mixing board. You systematically reach out and start isolating tracks. You mute the brass section. The feedback is still there. You mute the guitars. Still there. You are mathematically silencing the noise of the other variables. You hold them constant.
Let's apply this to a real-world scenario from the psychological literature. Researchers wanted to know what accurately predicts a high school student's performance in a rigorous critical thinking course. They measured 3 distinct variables: the student's final grade in the class, their raw cognitive intelligence, measured by IQ, and their need for cognition, that trait we discussed earlier, measuring how much a person intrinsically enjoys complex thought.
When they ran a simple correlation matrix, the results were muddy. Both high IQ and a high need for cognition were positively correlated with getting a good grade. The brass and the guitars were both playing loudly. The assumption would be that raw intelligence is the driving factor. Smart kids get good grades.
But then they applied multiple regression. They statistically muted the intelligence variable. They told the computer algorithm, show me the relationship between the need for cognition and the final grade, but only look at students who possess the exact same IQ score. Hold intelligence completely constant.
They isolated the track. And when they removed intelligence as a fluctuating variable, the truth emerged. Intelligence was not the primary engine of success in that specific class. Even among students with the perfectly average, identical IQs, the ones who genuinely loved the process of thinking dramatically outperformed the ones who didn't.
The regression analysis proved that the internal drive to engage with complex ideas was a more powerful predictor of success than raw brain power. Multiple regression allows researchers to rule out specific third variables one by one. It doesn't offer the absolute ironclad proof of a controlled experiment, but it allows us to build a highly robust, statistically defended case for a causal relationship.
It is a stunning triumph of mathematics. It lets us see through the noise. But as we move deeper into understanding human beings, we hit a philosophical wall. Up to this point, every single thing we have discussed has been quantitative.
Everything's been numbers.
We have been reducing the chaotic, beautiful, tragic reality of human existence into a series of numbers. We've turned people into dots on a scatter plot, into variables in a regression equation, into points on a volume dial. But what happens when an experience is so profoundly human, so complex, that reducing it to a number actually destroys the data?
That question forces a paradigm shift into qualitative research. The distinction between quantitative and qualitative research is not just a difference in methodology. It is a fundamental difference in epistemology, how we believe knowledge is best gathered.
Right.
Quantitative research seeks breadth. It wants a shallow measurement from a massive population. You want 10,000 people to rate their daily anxiety on a scale of 1 to 5 so you can run a multiple regression analysis and find societal trends.
Qualitative research sacrifices breadth for immense depth. It doesn't want 10,000 people checking boxes. It wants 10 people speaking unfiltered, messy, contradictory truth. It aims to capture the subjective, lived reality of the participant in their own unique vocabulary.
Because the goals are different, the tools must be different. A multiple-choice survey is useless if you don't even know what questions to ask yet. Qualitative researchers rely heavily on interviews, specifically unstructured or semi-structured interviews.
Think about the Lindquist study on the families of suicide victims. This is an arena of human suffering that is almost impossibly sensitive. If a researcher approached a grieving mother who recently lost her child and handed her a clipboard with a quantitative survey asking, on a scale of 1 to 5, how much guilt do you feel? It would be profoundly inadequate, clinically cold, and bordering on offensive.
Beyond the ethical insensitivity, it is scientifically flawed. A rigid survey assumes the researcher already knows the parameters of the grief. Lindquist recognized that he did not know what these families were experiencing.
So the researchers used unstructured interviews. They did not bring a list of standardized questions. They brought a recording device, an empathetic ear, and a very broad opening prompt. They allowed the grieving families to dictate the direction, the pace, and the emotional contours of the conversation.
They created a space for the participants to define their own variables. But this creates a massive logistical problem for the researcher. You leave that house with 6 hours of audio recordings. You have pages and pages of rambling, emotional transcripts.
You cannot plug a tearful anecdote into a multiple regression matrix. How do you extract scientific meaning from a conversation?
You utilize non-statistical analytical frameworks, such as grounded theory or thematic analysis. Grounded theory is exactly what it sounds like, building a theory from the ground up, rooted entirely in the raw data, rather than bringing a pre-existing hypothesis to the table.
The researchers sit with the transcripts, they read them, reread them, and read them again. They highlight phrases, look for emotional beats, and search for recurring ideas that pop up across multiple different interviews. The text is the data.
A poignant example is Abrams and Kern's qualitative study on postpartum depression among low-income mothers. They conducted deep, semi-structured interviews with 19 women. Through rigorous thematic analysis, the researchers distilled hours of conversation down to a set of core recurring themes.
One of the primary themes they identified was perfectly encapsulated by a direct quote from a participant they called Destiny. The theme was titled, "And you're telling me not to stress."
Think about the power of that specific phrase. It captures a reality that a numbered scale could never convey. These women were navigating the immense hormonal and psychological weight of postpartum depression while simultaneously battling the grinding reality of systemic poverty, unstable housing, and a lack of childcare.
And when they sought medical help, well-meaning doctors were prescribing stress reduction as the cure. Destiny's quote highlights the crushing paradox of their lived experience.
By preserving her exact words, the qualitative research illuminates the why behind the whats. Quantitative data might tell us that low-income mothers have a 25% higher incidence rate of postpartum depression. That is important data. But qualitative data tells us what it feels like to be inside that statistic. It generates the nuanced understanding that allows us to design better interventions.
Pause and think about this for a second. Let's frame this with a hypothetical scenario. Imagine you are tasked with studying the psychological resilience of young girls who play in highly competitive, male-dominated youth baseball leagues. If you only use a quantitative approach, you might send out a survey and find that 80% of the girls report feeling moderately accepted by their male teammates. You publish a paper saying the environment is generally positive.
But if you sit down and conduct qualitative one-on-one interviews, you hear the actual narratives. You hear the story about the opposing coach who demanded a birth certificate check. You hear about the silent, nuanced ways they have to modify their behavior in the dugout to avoid being labeled bossy. You capture the specific, fierce pride they feel when they strike out the biggest batter in the league.
The qualitative data reveals the invisible social architecture of the baseball diamond. Quantitative and qualitative are not competing methodologies. They are deeply complementary. The deep, messy human stories generate the complex theories, and the massive, sterile data sets test those theories at scale, which transitions us perfectly into our final arena of methodology. We've talked about asking people to fill out surveys, and we've talked about asking them to tell us their stories. But what about when we stop asking entirely? What about the science of simply watching?
Observational research strips away the interaction. It relies on the researcher's ability to systematically record behavior as it naturally unfolds. The most recognized form is naturalistic observation. This is Jane Goodall sitting quietly in the forests of Gombe, meticulously documenting the tool-making behavior of chimpanzees without interfering in their social hierarchy.
Or a developmental psychologist sitting quietly on a bench at a chaotic preschool playground, tallying how many times a specific child engages in cooperative play versus aggressive play over a swing set. The goal is to be invisible, to observe the subjects in the wild, uncontaminated by the artificial environment of a laboratory.
If a researcher cannot be invisible, they might utilize participant observation. This involves the researcher actively infiltrating and becoming a functional member of the group they are studying. We discussed David Rosenhan earlier. When he and his colleagues faked their way into the psychiatric wards, they were conducting disguised participant observation.
By becoming patients, they gained unparalleled, intimate access to the internal mechanics of the hospital from a vantage point the staff would never reveal to an outside inspector.
We also have structured observation, where a researcher carefully designs a specific situation, often in a laboratory setting, and watches how participants react to the stimuli. And archival research, where the observer isn't looking at living people, but at the traces they leave behind, analyzing 100 years of marriage licenses or census data to track societal shifts in age demographics.
But I want to spend our remaining time dissecting one specific, highly controversial and profoundly famous type of observational research, the case study.
A case study is an exhaustive, intensely detailed observational analysis focused on a single individual or a remarkably small group. Instead of finding a shallow trend across 10,000 people, a case study attempts to understand every single facet of one unique person's existence.
And the history of psychology is practically built on the backs of famous case studies. John Watson's Little Albert study, where he observed the fear conditioning of a single infant. The heartbreaking case of Phineas Gage, the railroad worker who had an iron rod driven through his skull, surviving but with a drastically altered personality. And, perhaps most famously, Sigmund Freud's detailed case study of a woman known in the literature as Anna O.
Anna O was a patient suffering from a staggering array of severe physical and psychological symptoms, including paralysis, hallucinations, and a profound hydrophobia, an absolute terror of drinking water. Freud, working with her physician Joseph Breuer, wrote a meticulously detailed case study outlining a specific theory.
Freud claimed that under hypnosis, Anna recalled a deeply repressed, disgusting memory of seeing a dog drinking from a glass. Freud theorized that the repression of this traumatic memory was the engine generating her physical symptoms. According to the case study, once the memory was brought to the conscious surface and the emotion was expressed, her hydrophobia magically vanished. It became the foundational text for psychoanalysis.
And this is where the rigorous methodological critique must be applied. From the standpoint of internal validity, the Anna O case study is a disaster.
Yeah, I have to push back hard on Anna O. The textbook even notes that Freud's conclusion is essentially worthless as scientific evidence. We have absolutely no way to verify if the memory of the dog was real or if the hypnosis implanted a false memory, much like Loftus did with the shopping mall. We have no way to prove that the repressed memory caused the hydrophobia. The relief of her symptoms could have been entirely due to the placebo effect or the simple passage of time. The internal validity dial is set to absolute zero. You cannot generalize the mechanisms of Anna O's mind to the rest of the human species based on one unverified observation. So why do we even care about case studies?
That is all entirely true, and your pushback is completely validated. And yet, case studies remain a vital component of this scientific ecosystem. To understand why, we must return to the distinction between verification and generation. Case studies are scientifically worthless for verifying a causal theory. You cannot prove a hypothesis with a sample size of one.
But they are unparalleled engines for generation.
Precisely. Freud's meticulous, albeit flawed, observations of Anna O generated entirely new paradigms of thought regarding the unconscious mind, the somatic manifestation of trauma, and the therapeutic potential of talk therapy. The case study didn't prove the theories, but it gave the next century of quantitative researchers specific, highly detailed ideas to actually go and test. They pushed the boundaries of what we even know to ask.
It also comes down to the grim reality of rare conditions. Let's look at the patient known as HM. In the 1950s, HM suffered from debilitating seizures. To cure him, surgeons literally removed his hippocampus. The seizures stopped, but he completely lost the ability to form new declarative memories. He was frozen in time. He can meet a doctor, have a conversation, leave the room for 5 minutes, and upon returning have zero recollection of ever meeting them.
If the scientific community rigidly demanded a large sample size and a randomized controlled trial for every piece of published research, we would have learned absolutely nothing from HM. You cannot recruit 500 people and surgically remove their hippocampi to run a regression analysis. HM was, functionally, an N of 1, a sample size of a single human being.
But by conducting an exhaustive case study on HM over decades, testing him day after day, year after year, researchers discovered that while his declarative memory was destroyed, his procedural memory remained intact. He could learn how to trace a star in a mirror, improving his physical skill day by day, even though he had no conscious memory of ever practicing the task.
That single case study revolutionized our understanding of the architecture of the brain, proving that different types of memory are localized in completely different neural pathways. The extreme, unique edges of human experience, documented through case studies, illuminate the normal functioning of the system in ways that sweeping surveys never could.
We have covered an immense amount of methodological ground here. Let's do a rapid-fire recap of this journey. The goal of this deep dive was to expand your understanding of how psychologists actually gather the data that fills Chapter 6 of your textbook.
We started by clearly defining non-experimental research. It is any scientific inquiry that lacks the active manipulation of an independent variable. While this lowers the internal validity, meaning we cannot cleanly establish cause and effect, it is an absolute necessity due to the ethical constraints of studying humans and the practical need to observe behavior in its natural habitat.
We looked at the blueprints for tracking time, the cross-sectional studies that give us fast data but fall into the trap of the cohort effect, the longitudinal studies that give us pure data but take a lifetime to complete, and the brilliant compromise of the cross-sequential design, mathematically isolating aging from generational shifts.
We dove into the math of correlational research, visualizing the swarm of data points on a scatter plot, and measuring their gravitational pull with Pearson's R.
And we mapped the minefield of statistical traps. We saw how Pearson's R goes completely blind when faced with a curved, nonlinear relationship like sleep and depression. We saw how restricting the range of your data can falsely erase a massive trend. And we hammered home the golden rule correlation does not imply causation, because you never know if the arrow is pointing backward or if a hidden third variable is pulling the strings.
To combat that third variable, we explored the realm of complex correlations, using correlation matrices to view the web of behavior and multiple regression to mathematically mute the noise and isolate specific predictors.
Then we shifted paradigms entirely. We embraced the qualitative approach, acknowledging that numbers cannot capture the depth of grief, trauma, or human resilience. We saw how unstructured interviews and thematic analysis allow researchers to build theories from the raw, unfiltered words of the participants themselves.
Finally, we analyzed the power of the observer, from naturalistic observation in the wild to the intensely detailed focus of the case study, vindicating its role not as a tool for proving theories, but as a vital generator of new ideas.
It is a massive, complex toolkit designed to study the most complex organism on the planet. And as you continue your course reading, keep these tools in mind. Remember, this audio deep dive is designed to be your companion, to provide the analogies and the narrative framework to help you synthesize the material. But it does not replace the intricate details waiting for you in Chapter 6. The specific charts, the historical dates, the granular definitions, those require your eyes on the page.
As we conclude our exploration today, I want to leave you with a provocative thought for the week. Turn the lens of observational research onto your own life. We are all amateur psychologists, constantly observing our own behaviors and drawing conclusions. Look closely at the patterns you have established. Think about a specific habit that you are absolutely convinced is causing your daily stress, or, conversely, a rigid routine you believe is the direct engine of your academic success.
You've identified the correlation in your own life, but are you certain of the direction?
Take a moment to rigorously question your own internal validity. Is that habit truly the cause? Or is there a hidden, unexamined variable Z, a third variable in your environment, your relationships, or your underlying health that is secretly dictating both your behavior and your stress levels? When you realize the X-ray machine is broken, you're forced to look much deeper into the shadows. Keep your eyes open and question your assumptions.